Okay. Welcome to the second session of this conference. The session will be about communication and network next generation. The first paper that we will start with is titled with a novel millimeter wave depicted ground structure based microstrip antenna for 5G cellular applications. That was written by Abdullah Qayyum, Arbab Hassan Hasib Khan, Shahabuddin, Uwais Ahmed, and Janshir Khan and Shahid Bashir. Abdullah Qayyum will present this paper. Please, Abdullah Qayyum, go ahead.
Okay, let me unmute. Ask to unmute. Abdullah.
Abdullah Qayyum.
Okay, he's unmuted now.
Okay, Abdullah, you can start. No, he's muted again.
Yeah. I have given him access to unmute. Abdullah, please unmute yourself and share your presentation. You need to click on the microphone to unmute.
Welcome, Abdullah. You can start.
Yes. Isn't my time 11:40?
Yeah, we are going to start now because we started the session early.
Okay, no problem.
Are you ready?
Yes.
Okay. So you can share your presentation.
Okay. Can you see the screen?
Yes. Can you make it in a presentation mode?
Yes. Hello everyone. I am Abdullah Qayyum, and today I am going to present my paper, A Novel Millimeter Wave Defecting Ground Structure-Based Microstrip Antenna for 5G Cellular Applications. The authors of this papers are mentioned. It's me, Abdullah Qayyum, Arbab Hasib Khan, Shahabuddin, Awais Ahmed, Jansher Khan, and Shahid Bashir. This presentation is organized in the following parts. First of all, I will talk about a brief introduction of the authors, our aim and objective in this paper. I will little bit discuss about the antennas, and then we'll talk about microstrip phase antenna, and then our design, and then this presentation will be concluded. So first of all, I will introduce myself. I have completed my electrical engineering with majors in communication from the University of Engineering and Technology, Peshawar, Pakistan in 2019, and currently I am enrolled as a master's student in Chongqing University of Post and Telecommunication, China. My other three partners, Arbab Hasib Khan, Shahabuddin, and Awais Ahmed, has also completed their electrical engineering from the same university in 2019, while Jansher Khan has completed his MS degree from Turkey with distinction. Our research was supervised by Dr. Shahid Bashir, who is assistant professor in the Department of Electrical Engineering, University of Engineering and Technology, Peshawar. So now let's come to our aim and objective. Our main objective was to design a dual band microstrip antenna for 5G applications that we chose the bands 28 GHz and 38 GHz that fall in the range of millimeter waves. So we wanted to design and simulate this antenna using CST Microwave Studio 2015. So now let's talk about antennas. Antennas can be defined as a mean for radiating or receiving radio waves. We can say that antenna act as eyes for the wireless system. Uh, uh, the formal definition of the antenna is any device that convert electronic signals to electromagnetic waves and vice versa with the minimum loss of signals. So, but we have to keep in mind that antenna is a passive device. It does not amplify the signals, but it just directs the signal in a specific direction. You can see different types of antennas in these slides like wire antennas, aperture antennas, and microstrip antennas, etc. So now let's come to the microstrip antenna. Microstrip antenna has gained it's become very popular in the recent decades, but it was discovered in 1972 by Bob Munson. These antennas are preferred because of their small size, low profile, low cost, and ease of manufacturing. So a typical microstrip antenna contains a patch, a ground plane, and a dielectric material in between these two. You can see a typical microstrip antenna in this slide. On the bottom, we have the ground plane, and above the dielectric substrate, we have the patch. Both ground plane and patch are made up of conducting material like copper or gold, etc. So the patch that is on the top of the dielectric substance can have different shapes that you can see in this slide. We have used the circular ring shape in our project in this paper. So we have designed this antenna in a simulation tool, and the simulation tool we have used for our research is CST Microwave Studio. The purpose of using a simulation tool is that it provides virtual prototyping of your model before going to the experiment, so it saves our time and cost uh, drastically. So now I will talk about the substrate material that is also known as dielectric material we have used for our antenna. We have used the dielectric material RT5880 that is specifically designed for the band for the Ku band frequency. It has low dissipation factor, so we have used this in our design. So now I will talk about our design that we have presented in this paper. First of all, we designed a simple circular patch antenna and optimized it for 28 gigahertz, so it resonates at 28 gigahertz. After it was optimized, we insert a ring-shaped DGS in the ground plane that is not exactly below the patch but slightly towards the feet. The position of the ring was adjusted after parametric analysis so that we have two bands, one at 28 gigahertz and the other one at 38 gigahertz. In this slide, you can see the front and back view of our antenna. In the front view, you can see the patch and the feed line, and in the back view, the ring-shaped DGS and the ground plane. So their dimensions of our antenna are shown in this slide. The radius, the patch is circular, so it has the radius of 1.9375 millimeter, patch height and ring shape width, and all the dimensions of the antenna are shown in this slide. The results we have obtained as our research, this antenna operates at two frequencies, 28 gigahertz and 38 gigahertz. The bandwidth at 28 gigahertz is 0.87 gigahertz, and at 38 gigahertz we have the bandwidth of 1.07 gigahertz. The S11 uh, um, value is minus 27 at 28 gigahertz and minus 15 at 38 gigahertz, and the gain is 6.87 and 4.17 at both the frequencies respectively, which are all the acceptable ranges. So now I will conclude my presentation that we have designed a dual band microstrip antenna for 5G cellular applications, and this antenna operates at 28 and 38 gigahertz. That's all from my side. If you have any questions, you can ask.
Thanks, Abdullah. Uh, Anyone have a question? Please raise your hand. Seems there is, haven't seen any question.
Thank you very much for
So
your
can
attention.
I ask myself some questions?
Yeah, sure.
Yeah, just wondering what's the dielectric constant, the RT Droid 5880?
You are asking about the value?
Yeah, the value of the dielectric constant. And
I exactly can't remember the value, but as I have told you that it is designed for the higher frequencies, so that's why we preferred it.
okay. But okay, have you used any like mathematical equations in for the DGS, defective ground plane structure? Is there any
No,
equation, or just like parametric and trial and error?
yeah, we use trial and error
Okay.
method.
You didn't show the radiation pattern and the side lobe level of the antenna. So do you remember what was the side lobe of the antenna?
Side lobe levels, actually, I can't remember the specific values at the moment.
Okay, then just last one is like a suggestion, if it's possible. Have you tried to make it reconfigurable to transmit one frequency at a time?
No, but we have suggested it as a future work that it can be used as a MIMO and reconfigurable antennas. We have suggested it for the future work.
Okay, thanks. That's from my side. So let me
Thank
see
you.
if there is anybody. Seems there is no more questions. Thanks, Abdullah.
Thank you.
The second paper will be by Prof. Rafael Nask. It's titled it's titled the application of future 6G technology to support heavy data traffic in highly mobile networks. Prof. Rafael is a professor and researcher at the Applied Computing Graduate Program at University Vale do Rio dos Anjos in Brazil. And welcome, Prof. Rafael. Please, could you please, Prof. Anis, unmute Prof. Rafael? Prof. Anis?
Yes.
Could you please unmute Prof. Rafael Nast?
Okay.
Hopefully I was saying the name right. Hopefully I was saying the name right.
Yes, you did.
Okay.
Thank you very much. Good morning. Let me share my screen here. Just a second.
Is there any issue with sharing screen?
I'm trying to share here. I think it's going to work now.
It's working now.
Can you see my presentation?
Yeah, you can start.
Okay. So I'm going to present the paper application of future 6G technology to support heavy data traffic in highly mobile networks. As I said, I'm currently a professor of computer science at Unicinos University in the very south of Brazil, and this work was conducted in cooperation with another university here in Brazil and with some partners from the Chinese Academy of Science. It's important to start mentioning of 6G technology. The main motivation of this paper is that the emerging and future applications will demand a lot of the network. They currently do in 5G, but we think they will demand even more network research in the future. So one example we can cite here is the real-time surveillance, which is the scenario that we are going to explore in this paper. So 5G partially deals with this increased demand for network resources, but recent research showed that the envisioned future applications will demand even more from the network, as I just said, and that's our motivation to justify the need for 6G. And in this paper, we evaluate the performance of 6G technology, considering a scenario where a mobile drone swarm captures high-definition images of a crowd and searches for a suspect in real time. This particular scenario involves collecting and transmitting large amounts of data to a cloud-based infrastructure. And as we'll see later, the scenario is challenging, especially when we want to guarantee some quality of service aspects for this real-time application. So our main goal here is to simulate the scenario and obtain initial results considering 3 quality of service related metrics. The main contributions of our paper is that we were capable of modeling the 6G channel capacity, which the main thing we did here is to calculate the channel capacity. And to do that, in order to do that, we consider a simplified model and some network parameters. As we are going to discuss better in a few slides, but it's important to mention that this is a seminal work, so we have initial results with a simple model at this time, but we are working to improve this model and obtain better results. Our results compare the previous generations with what we expect to be the 6G technology. So to understand our simulation parameters, it's important to go through some aspects of what is expected to be the 6G technology. And basically what it's going to be is an integration of 5G with satellite networks. And to do that, we are going to need to use high frequencies, and that will provide us with wide bandwidth. Of course, many aspects of 6G are still open. That's why we are researching it. But to obtain our results, we consider the current FCC recommendations. And in this sense, the FCC recently approved the use of 4 spectrum ranges, all above 95 gigahertz. And our case, in our simulation, we considered the last one in this table, which provides 2 gigahertz of bandwidth, but these frequency ranges provide us with up to 7.2 gigahertz of bandwidth. Here we show some related work. Currently, the research is mainly focused on identifying the challenges and studying transmission in high frequencies. But there are research also studying the enabling technologies for 6G, the possible architectures for implementation of 6G, and the challenges to implement these architectures. In particular, our work in our particular work, we defined a specific application where 6G may be needed, and this application considers the simulation of the existence of a high amount of UAVs that are moving around the city to identify suspects of a crime, as I mentioned before. Each UAV is equipped with a high-definition camera, and is capable of communicating with a private cloud to send these images, the images that are captured. The cloud processes these images and returns the information about the suspect to the UAV. So this involves obtaining the images, querying the database in the cloud, and all of this done in real time. So of course, this is a data-intensive task, and it requires some quality of service-related guarantees. So let's talk about our simulation setup. We create an analytical model that we implemented in MATLAB, and we use the parameters shown in this table, which are mostly based on an IETF specification. So for a media codec, we use VBR. The bit rate range goes up to 4 megabits per second. We use a high definition video with 30 frames per second and a maximum responsiveness to new bit rate of 100 milliseconds. We also consider channel bandwidth related parameters. As I mentioned before, our goal was to simulate the channel capacity in order to obtain the first results regarding the 6G technology. So all the parameters here are the typical values for 4G and 5G. And in the specific case of 6G, as I mentioned before, we consider the 2 gigahertz bandwidth following the specification of the FCC. And we model our network with no cells. This is because one of the possible architectures for 6G do not consider the existence of the traditional cell-based model of the previous generations. Instead, it will implement the concept of smart surface supported by tiny cells and temporary hotspots that can include hotspots mounted on UAVs or balloons. So each simulation was 100 seconds long, and we varied the number of UAVs considering the QoS metrics, as we are going to see in the results. We obtained results for 3 QoS related metrics. The first one was latency. In this case, we calculate latency as the round-trip time of a package transmitted from the UAV to the base station or the gateway. As we can see, 6G performs much better than the remaining technologies. It's capable of reducing the latency up to 93% in comparison with 4G and 89% if we compare to 5G. Also, we can see that in a situation with up to 1,400 drones, the latency in these simulations in our scenario is kept under 1 millisecond, which is the expected limit for the round-trip time in 6G network. So we can see that in this particular QoS-related metric, 6G performs very well. The second result refers to the delay metric. In this case, we measure the delay as the time a package takes since it's generated in an UAV until the gateway processes it, considering both the transmission and the processing times in this particular case. And considering a delay limit of 150 milliseconds, which we got from a Cisco recommendation, we can see that 6G supports up to 5 times more drones than the existing technology. In this case, 6G is the blue line, 4G is the green line, and 5G is the black line. So As we can see, considering the 150 millisecond limit, 6G supports up to 1,300 UAVs, while 4G supports ultimately. The final metric we consider here was the jitter. And here we consider a typical jitter value of a limit of 50 milliseconds, also using the Cisco document as a basis. And here 6G supported up to 1,200 UAVs, what's also more than 5 times better than 4G. And in this case, about 3 times more than supported by 5G. These results show the potential of 6G network to support heavy data traffic and still guarantee quality of service requirements of our current and future applications. So in this paper, we discussed the possible future real-time application of 6G. And to do that, we created a simulation model based on channel capacity and evaluated some quality of service related metrics. Our results show the potential of this novel technology. And as I mentioned before, since it's a seminal work, there is yet much more to come. So we are currently working on our future works, and they can involve profile on particular frequencies. And of course, here we evaluated only one of the frequency ranges that were reserved by the FCC, so we can improve our simulation model to consider also the remaining frequencies and also to support novel architectures for 6G implementation. Thank you very much. Now I'm open for questions.
Thanks, Prof. Rafael. So any question from the audience? Please raise your hand.
Okay, just maybe I have one question because I have seen here that you have made a comparison between 6G, 5G, and so on. So now we know that the design purpose of 5G was to reach the 100 millisecond delay. So what is new in the 6G? Because now, according to your experiment, you would like to reach also the 1 millisecond delay. Is there any difference? And why with 5G you find much higher delays as the target values that is 1 millisecond in your scenario, I mean?
You are talking about the latency in this case, right?
Yeah, the latency, yes.
Yeah, so we consider the 1 millisecond round trip time in this case, which is expected for the 6G. So and for 5G, let me play here. For 5G, we were not able in our simulation to keep the values below 1 millisecond. We got here, it's the black line in this graphic. It was between let's say 2 and 4 milliseconds. So in our results, it showed that 6G could really keep the values below the 1 millisecond marker. I don't know if I got your question right, but
okay, yeah.
Okay.
That's okay. Thank you.
Thank you.
Okay, I think it looks there is no more questions. So we will move to the third paper titled with avoiding forward loop across multiple domains without controller synchronization in SDN. So as requested, I will play the video first, then Dr. Zahid Khan will be available to answer any question from the audience. Give me 1 minute. Okay. Can you see the screen?
Yes. Yes, we can see. Dr. Saad, you need to reshare again the screen. And there is because we cannot hear the voice. There is an option that is.
Yeah, the voice from the recording is very, very low.
No, just make and share the screen.
Okay,
and
I will do it.
And when you share it, okay, so maybe I try to share it from my side, because there is an option that you need to enable the voice, internal voice.
Okay, then go ahead. Share it from your side then.
Okay, so I will do that. So it is avoid this one. Okay. It is loading. Okay, I will share.
Okay, go ahead.
Yeah, I need to enable share computer sound. That's what was missing. So now it should work.
Okay.
Today I'm going to present my paper that avoiding forwarding loop across multiple domains without controller synchronization in STM. My name is Noman Khan. I am doing PhD from University of Malaya, and my group member is Rusli bin Saleh, also from University of Malaya, Department Computer Science and System and Technology, University of Malaya, and my other group member is Zaid Khan and Professor Anis Kukaba from Computer Information Science, Prince Sultan University. So it's the outline of my presentation. It's the first introduction, then background, work, motivation, problem statement, and then propose as my scheme, that the simulation results and discussion conclusion. So first I introduce the basic architecture of STM. So it's the emerging architecture which is dynamic, manageable, cost-effective, and adaptable, making it ideal for the high bandwidth dynamic nature of today's application. So as we can see, the traditional network device is that the data plane and control plane, management plane are tightly coupled together, and they have these devices have their specific vendors. So the vendor just manipulate the data plane through the control plane, like through the routing, specific routing protocols and different type of applications. So the third person and other user have no authority to manipulate the data planes. And so it's become rigid and less innovative, because these vendors have very few, and they are just able to do such tasks. But the SDN architecture make open the door for the other users, and for the network operators and engineers, so they have controlled their network according to their own business need and made their own applications according to their network. So here we can see they just decouple the control plane and data plane. The control plane basically interact with data plane through open flow protocol, and that's through the southbound API. And the management plane interact with the control plane through northbound API. So on the management plane, they just install their own application and control their data network, whole infrastructure according to their own need. So it's make it directly programmable and abstract underlying infrastructure information. So here we can specify the purpose of our paper, that we have find the specific problems. It's the reachability failure in the interdomain. So the reachability failure, basically the packets of flow do not ultimately reach their destination, and the causes of this reachability failure due to forwarding loop and packet drops in the network. And the forwarding path forms a loop such that packets of the flow will ultimately be forwarded to their originated domain. Due to non-update of control plane, if loop exists, a single loop frame is sufficient to decrease the performance of entire network by consuming the bandwidth and CPU power of the affected device. and also become the packet drops is also occurring in the network. So this is the problem.
Dr. Anis?
To feasible the inter-domain routing, like between different domains, and it avoid forwarding loops and packet drops and maintain end-to-end service across whole network. So here we can see the hierarchical architecture and flat architecture. In the hierarchical control design, we can see that we have two domains, and every domain have their own controller. And in this topology, in this one are the slave controller, and this one is the master controller, also known as root controller. So these slave controllers synchronize their topology informations and about domain other informations time to time with the root controller. Is there any update in the data plane infrastructure layer? So they update it to the root controller through the slave controller. So if, for example, one person in the one domain talk with the other person in other domain, so this domain, this controller have such information about their own domain. So when they receive the flow request from their domain about the destination IP address, which is from different domains, so they send request to the root controller, and the root controller know all the information of the whole network. So they calculate the whole path from source to destination and install the update through the slave controller, the flow update sent to the slave controller update the data plane. So here the hierarchical control design work, but it's make a little time extra for the flow update, because it's during the sending the flow request to the root controller and receive the acknowledgement from the root controller, which take a time. So here we can see the flat control architecture. So here it's the peer-to-peer communication, and the controller synchronize their own information of the domain information with each other. So every controller have know about the whole network information of different domain. So when the same situation happen in this architecture, so they know the whole, so it calculate the path from source to destination and install the flow rules across the path switches. So it's high scalable, efficient inter-domain routing, but it's complex, and the interaction of controllers and high cost deployment means if we see hierarchical controller, so we need extra controller for it. And wastage of resources, an ideal scenario means that if there is nothing happen in the network, like such cross-to-cross communication domain, so it like wastage of resources, because they are synchronizing their information, and it's also fault tolerant. If, for example, one in the flat controller design, if one controller is failed, so the another controller will take over the charge of their domain. So it's the motivations of my paper. We have 3 papers here. So the problem statement, basically the multiple domain are necessary for scalability in large open flow network, like on wide area network, metropolitan area network, which make the network stable, because that one controller have authority are not sufficient for example for the whole country network. So we divide the network into subdomains to make it simple and efficient for the processing, and if the few nodes, so the controller can act very fast and efficiently to control their network. So the two in the data, how data plane fault occurs. So the two inter-domain connection are required to improve the scalability in the data plane, like the two domains connect with at least 2 connection, because if one is failed, so other will work, so there will no disruption in the network. So however, the two link cause forwarding loop and packet drop problems in the infrastructure layer without controller synchronization. So it can create an issue of reachability, like from one domain have no reachable to the other domain host. So our schema will maintain end-to-end delivery service. It avoids the issue of forwarding loop and packet of the source domain controller keeps the one link active among multiple inter-domain links through its egress nodes. So it's the use case how the forwarding loop and packet drops occur. As we see, there's the user A and user B in the figures. If, for example, user A talk with user B, so user A send the flow request to the node A, and the node A check their forwarding table. If there is no matching IP destination address in their flow table, they send flow request to the controller A. So either I will forward it or drop it. So controller A check their forwarding table, and if they see that there is no such uh, destination address in their IP table, so they send broadcast out because they know that our egress not connect outside the network. So they send our broadcast in the open flow network. So after broadcast it, the ARP request, so that now they receive the RPAC, a unicast ARP packet, and they confirm that resolve the IP address, the destination IP address. So when they send a packet through the link 1 or link 2, it because the controller B have also incomplete information, it mislead the controller and make the wrong topology draw of their domain, and it may cause the packet drops and loop occur in the network. So the our scheme idea and mechanism. So here avoid loop test packet scheme idea. So we take the example from we see in the figure that the ship can found the bottom of sea through the echo and reply from the sound wave systems or the laser beam system. It detect the bottom of sea. So we here apply like this type of concept in SDN. So the controller send the echo packets and receive the reply packet from the infrastructure layer, so they know how from the delay rate they know that how much for the destination from the source. So here we can see the experimental topology. That's how in this network. So how the our scheme work, the test packets. So for understanding this figure, we can see the flow chart. If, for example, the controller receive request for no flow entry, it check destination in same domain. If there is no yes destination in same domain, so it install flows rules across specific switches to destination. If no, that's it check the connectivity to other domain from the outside the domain. So it also not occur. So it drop packets. If yes, then test packet using the interdomain link 1 to n links and store the RTT round trip time information of interdomain links in delay module of controller and compare the delay rate of round trip time for link 1 and n. If check that the first link is delay rate is less than the rest of the links, interdomain links, so its controller select link 1, and if controllers equal delay rate, so link randomly selected. If the last link is delay rate is less compared to the rest of the control, select link and install flows rules across specific switch to destination. So the simulation results and discussion. So here the simulation parameters. So we have parameters. Interdomain link 1 is 1 Gbps. Interdomain link is 512. Control topology is single. Data plane topology is mesh topology link latency, and interdomain link bandwidth routing algorithm is by default short path algorithm. OpenFlow is 1.3 version, controller is Open Daylight, and emulator is Mininet. The performance metric is test packets which the controller sent to the inter-domain links. So their round trip time and UDP throughput from the UDP source to UDP destination, and loss ratio and TCP throughput from the source to destination. So here we can see the delay time of test packet 1 and 2. So here is the test packet 1, round trip time is around 1370 round trip milliseconds, and here is the 13. So the difference between is 10 milliseconds. So the controller prefers the test packet 1 length, like link 1 in the figure. So here is the UDP performance result of path from S1 to D by using to inter-domain link 1. So that's the consuming bandwidth across the 300 time seconds, and it's the loss ratio across the time seconds, packet loss ratio, which is almost negligible. So is the TCP traffic from TCP source to destination TCP, and it's also show the Mbps through the time seconds. We use the IPR tool command to measure the throughput across the network. So its conclusion, avoid loops and packet drops is the main concern for the reachability in network. So we use it can reduce, our scheme can reduce the layer of controller architecture and maintain end-to-end services across the network, across the multiple domains in SDN. It can reduce deployment cost and complexity among multiple domains. It deploy more domains without affecting like the structure of our network, and like we will not synchronize the controller, so it's easy to deploy more domains easily. Future work, if for example the controller select the first inter-domain link using the test packet, so the other link will remain idle, thus the traffic flow congestion on the single link is possible. So in the future work we will use the load balancing among the links to make it to avoid congestion in the network. So the control disaster recovery is also a big challenge for the LTP solution. Multiple testing, it means that if the controller of particular domain fails and the communication with other domain will lose, in the future we will address this issue. It's not fault tolerant. So in the future we will address also this issue. So thank you to listening us, and I'm greatly thankful to you. If you have any query.
Thanks everyone. Thanks for the presentation. So Prof. Anis, could you please stop sharing the screen? And Dr. Zahid Khan and Nu'man Khan are available for to answer any question, if any, from the audience. Seems there is no questions about the presentation. So I do think, Prof. Anis, that we will have a break until 1 p.m.
Yes, we will have a break until 1 p.m. and then we will resume back, inshallah.
Okay, thanks everybody.
Thank you very much, Dr. Saad, for being the chair of this session. And thank you for everyone for being here. And let's resume according to the schedule at 1 p.m.
Okay, thanks.